Next, we have Ms. Mini TT, Technologist, Dell Technologies India, for our technical session.
Hello everyone. Today, this session, let us discuss about approaches to implement zero trust architecture in an embedded system. I am Mini TT. I work as a security technologist with Dell Technologies. We hear a lot about zero trust architecture, and usually what we hear is how do we apply the principles of zero trust architecture as seen from a network point of view. But if we go through zero trust architecture, they are more about principles. This session, we will look at how we can apply these principles in the context of an embedded system. When we say an embedded system, the context could vary from small devices to larger devices with higher computing abilities. And this session, we will discuss these principles and how to look at it inside the embedded system. We are not talking about from the outside as a box, but instead inside the embedded system among various modules, how do you apply these principles? If we look at a typical network in an embedded system view, we will see that there are different heterogeneous entities that are part of this network. On one end, we will see that they are the things shown in the left side of the diagram. And then those things will be communicating to various entities in the network, and it may reach to an edge gateway. And from an edge gateway, probably we might be talking to the applications hosted in a cloud or an internet boundary. So that is their boundary. And in all these situations, what we will see is the underlying hardware security is what we need to make sure. And the underlying hardware or the firmware running on top of the hardware, that's a platform that provides for acquiring security on all these components that are there part of the network. So when we look at zero trust architecture principles in this kind of a network, we will be talking about internet boundary, which you see it with a red line on the screen. And then there are local communication and applications on cloud, and that kind of a boundary is what we speak of. Whereas here in this session, what we will look at is inside the application or the inside the firmware in each of these embedded devices, which from the things to your wireless communication in the local or the underlying edge gateways, underlying hardware, or even when we talk of the cloud, they are hosted on servers in the data center. And then how do we acquire the embedded system security for the underlying hardware? So that's what we will be seeing it in today's session. And the needs are different. The security of the system and the applications, they depend on the underlying hardware and the platform which is provided by the hardware and the firmware. That's what usually we call it as an embedded system. So let's continue. Embedded system, they have different kind of challenges that we will see. We need some kind of a secure processing. And how do we achieve that? We could achieve those kind of secure processing by using secure computing architectures, like the underlying hardware provided secure computing architecture and the firmware provided and the system provided secure compute architectures. Like when I say, I'm referring to examples like secure boot that provides a good trusted execution scenario where the hardware and the firmware that is running is trustable, and attestation is the hardware or the firmware or that physical device coming from an entity or a manufacturer who claim that it is coming from, and is it running a good firmware, and is it having the time correctly, is it location correctly, or the underlying infrastructure is that good. That's what we are referring to by the attestation. And they could be realized by various kind of identities. uh, like last year session we had talked about device identity composite engines, or it could be any other TPM kind of identities. Those could be your secure processing and secure computing architecture that we are meeting those requirements. And the next is about power consumption. Those are also embedded system security challenges. How do we make energy efficient premises primitives? Those primitives could be algorithms that we choose. Say for example, ECC kind of algorithms will be much more faster compared to RSA algorithms. And especially another challenge that could happen in this environment is some of them are not always alive kind of devices. They'll come up sometime, they'll be performing its function, sending out its data, and then it will go back to sleep. So there are scenarios in this embedded system where some of them are sleeping almost all the time, will be getting up, sending some data and going back. And what kind of power efficient implementations we could use in those kind of scenarios? They could be, say, datagram TLS instead of our normal TLS that we are talking. uh, the DTLS provides certain ways of doing, like the DTLS handshake. Maybe we can use pre-shared keys. Those are mechanisms that we can realize this power efficient computation. And again, we have problems like network threads. How do we achieve secure networking? That is our other TLS, and identity based secure access control and authentication, what we are talking, all those will come into your secure networking. And tamper resistant systems, that's also something that we need. And for example, as we told in the secure boot just before, we will be using the e fuses that is burned into the hardware so that they are no more tampered. And the next kind of tamper resistant could be TPM kind of item, secure storage environment, where we could store the private keys in a tamper resistant environment. So in this, what we see is the kind of challenges that we face in an embedded system. And each of these challenges, and how do we apply the principles of zero trust architecture to meet these kind of security challenges, are seen from inside the embedded system box. We rip open the box, see inside what is there as you power on the SOC security, and the operating system, the bootloader, applications running. How do we acquire security in this scenario using the zero trust architecture principles? That's what we are trying to see here. So the kind of attacks that can happen from the scenario that we described before, this is a summary. I'm not getting into very details of the kind of attacks that could happen. Categories could be a side channel based attacks, or interception based attack where somebody is taking the traffic somewhere on the communication line, and then that could result into information disclosure, or there could be privacy concerns that can happen. Or it could be software based attacks, like when you are HTTP, HTTPS, or SQL injection kind of attacks that could happen. Or it could be interruptions by providing or denial of service kind of attacks that could happen on the communication, or even the performance of the device itself. Or maybe it could be resource exhaustion. All those kind of issues can happen in the embedded system. And other could be tampering, data tampering, and modification based attacks. All these could happen. These are the kind of issues that can happen as attack scenarios, but it's more of categories than very specifics. I would recommend that you can look up public resources to see more specifics of how these happen in these categories. Now let us look at the zero trust architecture principles. Here we will be seeing mostly related to what NIST is talking about. Many of them must be already knowing that NIST has published a document called Zero Trust Architecture. So most of these Zero Trust Architecture principles are based on what NIST is talking about. So the principles which are talking there, these are the kind of categories of principles that are put there. Like, one is that we should look at all the data and all the data sources and the computing services as are to be treated as resources. So everything is a resource in the context of the system. And communication, irrespective of the network location, regardless of where it is placed, we will have to look at all communication, and everything should be secured. So this is where some of the challenges that can happen in that inside the embedded system. Inside the embedded system, most of the time, how do we see? We see that till our network access point, till the kind of the Ethernet that line is coming in, we will look at the uh, secure communication. But when we look at inside, how do we do a bus protection? How do we do memory protection? Or even pointers? How do we use the pointer authentication so that only those kind of valid pointers are used? Like how to prevent somebody from exploiting, say, buffer overflow kind of kind of scenarios to uh, attack your system. Those are kind which can happen inside the system. So how do we create this kind of secure communication inside the system itself? That's what we are talking in the inside the embedded system context. So then another principle that is talked about is about per session based access. So that means you create a session and create granular access, reduce the scope of the session, create more granular sessions, and then allow access authentication only for that session which is granular. As I mentioned, when you look at from a larger network, those granular might be uh, till the information comes into the embedded system. But when we look at inside, we are still talking about, is it that specific process, or is it that memory area, or is it that kind of secure compute enclave? That's what we are talking there. And the policy based access is another topic that we are talking about. The policies are to be done dynamically. So dynamically policies in a network, in a larger network, it might be easier, but then things could happen that in a embedded system, having dynamic policies and then adjust the policies according to the dynamic state as what you observe how the system is going on, there could be challenges. In this session, I'm not proposing that there are not challenges in implementing, but it is more like how to approach the same principles when we design embedded system or when we go inside the embedded system. That's what we are trying to see. But there could be challenges, multiple challenges in realizing all the principles that we are talking about. And the next is more, you will monitor and measure how the system is performing. And we could use that information also for defining how these policies are to be adjusted dynamically. And authentication and authorization are dynamic, and they are enforced before access is allowed. That is another principles that is talked here. And then we have information collection. As much as possible, collect information on the current state of the asset, current state of system and the infrastructure and the communication, and use that for improving the security. So that is where this dynamic adjustment of policies and access control happen. Now let us look at policies, what we are talking. Policies is a focus area in the zero trust architecture principles. As much as granular access and the resources is to be treated as or everything, all compute resources to be treated as resources, including the task, the services, all of them. And then access apply policies and adjust the policies dynamically. That's what we are talking in the principles of zero trust architecture. And let us look at these policies. So from what we talked about, uh, see, let's come back to the story. You must have heard of the Alice in Wonderland story where she drinks the liquid in the bottle and suddenly she grows big and she grows small and then she can't reach anywhere. Uh, what's happening is, as she saw her drink me, she took it and drank it. But then the thought went through her mind that should I drink it or should I not drink it? So that is like, how do you apply your policies before you make a decision to act on that? So it was very well to say, drink me. But Alice knew that don't drink it in a hurry. I will see first whether it is marked poison or not. And she knows that there are a lot of stories where children got burned or maybe they were eaten up by wild beasts and many other unpleasant things happening because they don't remember the simple rules their friends taught them. So in this securities environment also, these policies appear to be simple rules, but then follow them, apply them before we allow access, before anybody is allowed into your system, or before the data is disclosed. And what the story is telling is, if you do not follow those, then it is almost certain to disagree with you sooner or later. So follow these principles. There are quite a lot of principles that we see in the security space. Many of you must have heard of them lots, like the principle of least privilege, principle of defense in depth, or authentication, authorization, all those kind of principles. So we are still talking about similar principles which are applied along with the zero trust architecture principles that are telling that, okay, you apply your policies and then only allow access. So let us look at how these components look in a zero trust architecture. So these are the kind of components that we are talking. If we see from this diagram, you are seeing it from a network point of view. You apply all your continuous diagnostics and mitigation information, all your compliance standards, threat intelligence, the information derived from the log, or the PKI, data access policies, all of that. And then say a subject is coming and then coming from an untrusted world and then coming to access a resource, which we are seeing there, which is a trusted, implicitly trusted environment. And when it is coming from the untrusted world, you apply the policies, enforce the policies, and if the policies are met, then you allow access. If the policies are not met, then you do not allow access. That's what we are seeing in the diagram. And the policy engine and the policy administrator, they are the decision point which makes a policy to allow or not allow. Or there could be other policy decision can be multiple, either you allow or maybe If it is some kind of systems where you do not want a downtime, you allow, but then you may log it for alerts, may be logged for seeing that there is something going on, or maybe you ignore it and then you continue access. All of that can be, or you totally quarantine the system and then do not allow access. That itself can be another policy that can happen, and dynamically adjust these policies. These policies being enforced before we start, that's what we are talking in this zero trust architecture components. So let's see, how do we implement this as a process? These are the principles. How do we go about doing it? So what we could do is first define what is a protect surface. That is, identify what is the data, application, asset, services, everything that we need to protect. And then they could have interdependencies where the traffic that is happening between those elements and the flow between them, and those identify and map those interdependencies so that we have a view on how this data flow is happening. And then identify the microperimeters. Microperimeters in an embedded system could be your secure compute enclave, maybe it could be your TPM, or where your encryption is performed, where your sensitive data is handled, or modules where your access control is done. All that could be your microperimeters. And then identify your granular controls and the specificity. Identify being specific about what control and the microperimeter for each of them. That's what we are seeing here. And then based on all this, you establish access control policies. Who can have access and how to establish the trust? Like, is it about a username password kind of authentication? Do we apply multi-factor authentication, or is it the kind of public key, private key based authentication, like your typical certificate based authentication, TLS authentication? Is like what kind of mechanism you use for establishing the trust? After that, once you are able to do all this, then once you deploy, then continuously monitor and optimize. There could be optimization could be coming from there could be issues that are seen, signs of issues. You take that and improve your policies, and the logs that you see, maybe you review the log and the intelligence gathered from all that, feed it back into allowing your policies and increasing more visibility and improve on the policies. That could be the process in which we implement this zero trust architecture. From a network point, that's what you will see in most of the public domain literatures. But then if you look at it from an embedded system point of view, uh, the concepts remain the same, but the elements that we apply, they could vary. Like as I mentioned, some of them could be bus protection, the internal buses, how do we protect, like the SPI bus or the I2C bus kind of items. And then it could be that, say there could be removable hardware component. When you remove and put another hardware, how do we know that they are good? And then it could be the secure keys, who has access to those keys. And say if you are doing cryptographic function, which software modules can have your cryptographic function performed. Those are all are the items that we'll see inside the embedded system. And let us see how this principle can come inside in a little more in a detail. So this is what we see in a traditional system. An embedded system, when we say traditional, we will see a processor down, then you will have your input output, then have your RAM communication interfaces, your PHY, ROM, all that, and then you have software modules built on top of that. That is your BSP, bootloader, drivers, maybe your HAL might be there, config files, the operating system kernel, application services. This is what you usually see when we look at a embedded system architecture. Now, if we apply your security principles and then enhance the system for security, then you will come into much more elements into this. We will see talk about secure boot. We will see secure storage in the embedded system. Like it could be a, as an example, it could be a TPM storing the keys, or the keys are generated inside. There could be random number generations, communication, secure communication. There could be fuses for burning fixed information. And similar to secure compute enclaves, there could be like examples of ARM trust zone, Intel SGX, all those kind of computer enclaves could be there. And we are talking of application isolation, stack protection, memory protection, bus protection, all that could happen when we are talking of security, seeing the embedded system from a security point of view. How do we secure the system? So all these orange boxes that you see there, they are items that you will see beyond what you see in a traditional manner for enhancing the security of the system. Considering that this is what is going to be the embedded systems architecture from a hardware as well as a firmware point of view, let us see how the principles which we spoke just before, that's the zero trust architecture principles, what mechanism can be used for realizing or superimposing those principles into this kind of a system. Now let us see how these zero trust architecture principles can be applied onto an embedded system. So when we apply that in the context of an embedded system, we have quite a lot of internal modules. You look at the diagram in the right. Usually when we say this access is coming in, and then everything inside the embedded system is an implicit trust zone. But when we apply this principle, what we do is we will create granular access inside the embedded system itself, and then we segment them into zero trust zones. So that is what we are talking as micro segmentation. And the segmentation could be between doing by using trusted computing base, trust between modules. There could be micro perimeters, all that could be happening. And as I mentioned earlier about secure boot is what we need in an embedded system to establish a fundamental foundation for starting the boot. This is even in a secure boot itself, we are still talking about establishing integrity and authenticity step by step. So on power on, the immutable code verifies the security of the authenticity and integrity of the first mutable code, which is typically the bootloader, and the first mutable code further verifies the next modules, say the operating system, application, all that. And that is how we establish a trusted environment in our system, that we make sure that the software, firmware, application running is uh, having its authenticity and integrity. So at each stage it is verified. And then we speak about identities. Identities are to make sure that is it coming from a right manufacturer, can we trust the hardware and the firmware which is executing in this, which could be realized by using multiple entities like random number generation, which are further used for key generation. So here what we see is these devices, they originate from a manufacturer, a personalization will happen, and identities are established, which could be a cryptographically bound identities, which are keys generated inside, and the keys never go out of the out of the system. That's what we talk about in the keys generated, and then they are bound to the hardware. There can be other mechanisms for realizing this, like say functions like puff, like which is bound to the hardware, like SRAM based puff. All those are possible. There are multiple ways to realize. That's not what we see here, but we are talking about the identities. And the next is something which you talk as the trusted execution environment. So usually what we see is protection of data at rest, data in transit, and data in use. By using your TLS, SSL, or by using encryption, we are able to do data in transit and data at rest. But when it comes to data in use, we are already talking of data which is not encrypted, which is in clear. So that is where we come into secure uh, computing enclaves. As I mentioned, Intel SGX or ARM trust zone kind of item. ARM trust zone defines a normal world and a secure world, and then you can switch between them. Whereas the Intel SGX, there are secure computing enclaves, and inside the enclave you have your enclave stack code and your entry tables and heap, and you can enter into the secure enclaves, finish your computation, and then come out, and no data is shared between your secure enclave and the non-secure world. And when it is shared, it's already uh, communicated in encrypted form, so that the normal world cannot make out what is the encrypted world data. That's the concept of implementing these secure computing enclaves. So when I talked about micro perimeters, these computing enclaves could be seen as your micro entities, or the micro resources which are doing this computation, and we could define perimeters based on this. And then this is another item that will come in the embedded system world. Say for example, a very composite devices. Say for example, some kind of industrial machines which have replaceable units as well as fixed units. Typically the CPUs could be your fixed unit, and then replaceable units could be other parts of it. Or in the present day, when the domain which I am talking about, the replaceable units could be your hard disk or your network cards. All that could be replaceable units. Or sometimes even the CPUs are also replaceable units when we talk of some kind of data center kind of environments. So here it is, the security is depending on the security of the entire assembly and not only on the individual items. So we'll have to make sure that the entire assembly is secure, and identity of each of the sub-components should be guaranteed, and they could be homogeneous, they could be heterogeneous, flat, hierarchical, various models can be there. And the hot swappable units, when we swap out and swap in, are we putting it back another trusted module, another module where we guarantee integrity and authenticity. So this is the mechanisms for enforcing your policy enforcement. We could take the device state and deviations from known patterns, the boot integrity, integrity of the subcomponents, then the integrity of the assembly in itself, all that could be seen. And then we define your policies. Say, for example, you remove and put another drive component, then do we really want to work with it? If it is uh, like say some things like attestation, you could attest to see that whether they are coming from a genuine manufacturer, is it running a good firmware, or all its from a security point, all its status, is it all good? If we see that it is not, then what do we do? So those are the policies definition. As I mentioned, it can be okay to the extremes of one is okay, I ignore it and continue to work with it, or quarantine and I'll stop working with it, or there could be various intermediate levels of enforcing policies. That depends on the environment in which you are operating. So till now, what we talked about was how to apply those principles of zero trust into this embedded system. But still, there is what we were seeing was even with the secure compute enclaves, we see that they are still we are reducing the attack surface by the granularity. We are making it smaller and smaller. But then, is that sufficient? So, can you make it instead of having this implicit trust? We still have not moved away from the concept of implicit trust. We still have this TCP concept which we implicitly trust. So I would still like to call it as an approximate zero. So can we move it more closer to the zero? That is when we call it a zero trust, not approximately zero trust, instead how to come to a zero trust in its true sense. That is where these kind of compute enclaves, what we see here, like I explained already, the Intel SGX and the ARM trust zone kind of compute enclaves from normal world and secure world. Can we use other mathematics based concepts for using your confidential cooperation so that we don't have to share the data itself? This is where other algorithmic methods come in, like secure multi-party computation or homomorphic encryption, or there can be other methods of split secrets, like Shamir secret sharing scheme, or homomorphic encryption is where we take your data and you compute over the encrypted data. And secure multi-party computation is like multiple people can do a computation without disclosing their individual data, but only the result is known to everyone. Like say in a medical setup, individual hospitals don't want to share their data, but they want to have the aggregation, say for example COVID, a pattern of the how it is happening across all the hospitals without sharing the individual data. This is where the next stage of cryptography based and these mathematical computation based items that we can use for confidentiality, that is multi-party computation, homomorphic encryption, split secrets, those kind of mechanisms. This is an evolving field. So as a summary, what we discussed is what are the challenges in the embedded system security and the principles of zero trust architecture, and how embedded system architecture is usually done, and how they are enhanced with additional security measures, and how to apply these zero trust architecture principles in such kind of an embedded system. And then finally, we also discussed about instead of reducing the compute base, how can we move away from this totally by using from the secure compute enclave point view to confidential cooperation kind of an environment. So this is what I had to cover in this today's session. Thank you for listening.